What if this guy jumped into my living room? Well, let me show you how I made this. We need to make a robot first. Let's ask ChatGPT. What if our robot is a star of a movie? What if we make a poster for that movie? The poster is looking cool, so let's go print it. I got this. Now let us put this on the wall. If you like the poster, there is a download link below. Now that we have the poster on the wall, we need to make a 3D model that is animated, and we'll be using a tool called Meshy.AI for it. I'll adopt the robot image we got from ChatGPT and then click generate, and boom, we'll have a model. We can choose which of these models we want Meshy to put clothes on, and Meshy will texture it for us. Our model is looking pretty good, but it has 195k polygons. And thankfully, Meshy allows us to remesh the model to reduce the number of polygons. And just like that, we are down to 10,000 polygons, and the model still looks pretty good. Now let's give this robot some moves by going to the Animate tab. Here, if you have a humanoid model, Mesh can really easily rig it for us. Once our model is rigged, we can choose from a pretty extensive animation library. I added all the animations I wanted. Now I can directly download them in USDZ format that we can use with Apple Vision Pro apps. You'll need to download a separate USDZ file for every single animation you have added to your model. Our model is looking pretty good, but I want to make it look more realistic. Now Meshy does provide some stylization options which can generate PBR materials, but that was making the robot look overly metallic. So I used ChatGPT's help again. I passed ChatGPT the diffuse texture and then asked it to generate other maps like roughness map or the metallic map, even normal map, and ChatGPT happily helped to do so. And these are the textures that I finally have. Well, that was a lot of work. For the AI, not for us. Now let us use these assets in Reality Composer Pro. I will add these files to the Reality Composer Pro project in my Xcode project. I have created a new scene here called Robot Scene, and I'm going to drag any one of our robot's USDZ files. The entity we just added has by default an animation library component which we can use to play the animations on the robot. We will only add one of these USDZ files to our scene and use the others to get the animations from. While we are here, I'll also rename this entity to robot. Now I will be adding a cube to the scene and make this the robot's parent. We are mainly going to use it so that we can detect the collisions with the floor. I'm making this cube super thin on the y-axis by changing its Y scale. Now let us try to rotate the robot. Uh-oh, our robot scale is all messed up because we have a non-uniform scale on the robot's parent. So to fix this, make sure you always apply any rotation transformations to your robot first, then make it the child of the robot parent, which is the cube. So now I have applied the correct rotations for the robot, and you can see that it's floating a little bit above the cube, so I'm going to drag it a little bit down and then make it a child of the robot parent. Speaking of the robot parent, I originally added it to detect collisions with the floor, so let me add a collision component here. Uh-oh, the extents on the robot parent, which is a cube, doesn't seem right. Maybe this is because the robot is the child of it. Let me fix it. To fix it, I'm going to remove the robot from the cube's hierarchy and then add the components to it. Now the extents are looking right. I'll now add a physics body component here and make sure that the physics body is kinematic, and I'll also disable the gravity on it. Let us not forget about the textures we created for the robot. So here I'm going to select the main material on the robot and add the textures we created. I think the emissive, the normal, and the roughness map give me the look that I'm wanting for the robot, so I'm not really using the metallic and the occlusion map here. The robot is now looking great. Now that we have done all that, let's make the robot a child of the cube again. Okay, so now this robot only knows one animation, and we can add the other animations from the other USDZ files that we have imported in the animation library component of a robot entity. So here I'm selecting them and simply adding them, and they all get added to the animation library. So now our robot has all the animations, and I have also renamed them so I can find them in Xcode. One cool thing about the animation library is that you can take an animation and you can chop it into pieces. So I'm going to do that for our jump. So our jump, when the robot kind of jumps out of the portal, what I'm going to do is I'm going to play half the jump, and then the robot is going to come down due to gravity, and when it hits the floor, it plays the other half of the jump animation. The cool thing is that you can split the animations right within the animation library component itself and rename them. Finally, I don't really want to see the tile here, so I'm going to make its material invisible. To make a material fully invisible, all you need to do is just change its opacity to 0 and its ambient occlusion to 0. Okay, so we need to teach our app how to track this poster. And we can do so using ARKit with 3 easy steps. Step 1. We tell our app which image to track. We need to first create an AR resource group where we can add our image. Then we can simply copy our image into this folder. Xcode is getting wonky here because it doesn't really know the dimensions of our physical image. So once we specify that here, Xcode becomes happy. So in my case, it is 34 by 26. Sorry, 24 by 36. Step 2. Tell our app what to do when it detects the image. We are going to use ARKit to track the images. So we are initializing an ARKit session over here. Then we initialize an image tracking provider where we pass it some reference images. Now here we are passing the AR images AR resource group that we just created. Any images that will be placed in here will be tracked by this image tracking provider. We have the run session function here that runs an ARKit session with the image tracking provider. Then we have this function called process image tracking updates. Here we can await for any image anchor updates from our image tracking provider. Here we can handle whenever our image anchor gets added, updated, or removed. We call the create image function whenever our image anchor gets added. Here, when we get the image anchor, we can determine the name of the image, also the physical size of the image that is getting detected. The scale factor tells us what is the difference between the dimensions we have provided in the AR resource group for this image versus what is actually being tracked. So if it matches 1 to 1, the scale factor is 1. Then we can use this information to generate a quad by passing it the width and height, and then create a model entity from that quad. We'll be saving all these entities that we are creating as the plane gets detected in some variables and also add that to the scene. And then finally, we apply the transform of our image anchor to this newly created entity. Whenever our image anchor gets updated, we apply the new transform to our existing entity from our entity map. And whenever this anchor gets removed, we simply remove it. Step 3. Start tracking the image. We can do this by creating two task modifiers in our reality view. One calls the run session function that initializes and runs the ARKit session. Second, we'll call the process image tracking updates, and it will start processing the image anchors as they come in. Also make sure that you're adding the world sensing usage description to your app, otherwise your app will crash. Let's see if this works. Where is our quad? Well, it's there. If we look at it from a little down, it's right there. Why is this happening? Well, can Xcode help me figure this out? Okay, so seems like the image anchor's y-axis points outward and the z-axis points downwards. That means I need to rotate my quad 90 degrees on the x-axis. I rotated our entity with the quad minus 90 degrees on the x-axis both in create image and update image, and let's see if that fixes the issue. Time to make the portal. Okay, so a portal is cool, but without the robot it's not really that much fun. So let's first try to add the robot in the portal as well. To do that, what we are going to do is we are going to find our robot from our Reality Composer Pro scene. Once you have found the robot, you call create portal world and pass the robot parent to it. Make sure you don't forget to add your portal world to your RealityKit content, otherwise you won't see it. To create the portal world, we need to create an entity with a world component. Then we load a texture for the skybox image. I already added a texture that kinda looks like the robot's home. If you're curious, I created this skybox using Skybox AI by BlockadeLabs. It's a really cool tool that allows you to create 360 images using AI very quickly. So once you have loaded the texture for the skybox, you'll create an unlit material with that particular texture, and then you create a model entity which is a sphere that has a radius of 10 meters and you flip it inside out. Once you have done that, you simply add the skybox and our robot parent to the world entity. Okay, so our portal world is ready, but we cannot see it through our quad. To do it, we need to replace the material on the quad with a portal material. Then we need to add a portal component to our quad with the portal world as its target. We then set the position and the orientation of the robot. Here we are doing the same thing to the robot that we did to our quad. We are assigning the image anchor's transform to it and then rotating it on the x-axis by 90 degrees. Let's hope this works. Uh-oh, our robot is kinda looking messed up. Alright, I can't seem to figure this out. Time for a coffee break. I think I know what's wrong. I think the issue is happening because our robot parent has weird scaling. So I'll unparent the robot for a minute. For the robot parent, I'll set the scale right and then reparent the robot. You can see that the robot is floating above the box now. So what I'm going to do is I'm going to pull the robot a little bit below. That seems to have fixed the issue. Now I just need to pull the robot a little bit down and push it a little further in the portal. I played with the offsetting and the scaling of the robot till I was satisfied. And while I was at it, I also created a platform underneath the robot. The portal just showing up is not fun. How about we make the user press a button and then the portal opens? Let us take a look at this effect first so it will make more sense as we implement it. I've created this scene here called Portal Material Scene. In this scene, I have a cube on which we have our material applied that is going to show the scanline effect, and then we also have two particle emitters here. The hierarchy here doesn't really matter because we are going to use all these things separately. The material here uses a custom shader graph that uses two properties. We have the scanline property here that goes from 0 to 1, and as its value increases, it burns the poster. And other is a texture here that just shows the image of our poster so that we can create the effect of the poster itself is burning. I do want to note that we are not hard coding this poster over here in the shader. This is just a sample of what the shader can use so we can visualize the effect. The shader is pretty simple. We take the Y value from our texture coordinates and subtract a remapped scanline parameter from it. And then we apply a step node to it. The step node gives us a very hard edge. We create a copy of that step node, but this time we'll add a simple offset to it. So when we take the difference between these two step nodes, we get a solid white line like this. I'm also using a smooth step node between the difference between our texture coordinates Y value and the scanline parameter and simply multiplying it with a red color, and that gives us this red looking glow. Then we add the white line and the red glow to create a blooming light effect. We multiply the output of this with some numbers, we can increase the intensity of emission. In the base color node, we are simply passing the texture as is. As the line is going down, we also want to make our poster disappear. And we can do that by taking the output of the first step node and simply passing it to our opacity and the ambient occlusion node, and that creates the overall effect. For the particle effects, I have added two particle emitters. We are going to animate these two particle emitters down with the scan line to create this burning poster effect. I created these particle effects from the impact and the sparks particle presets. Then I played a little bit with the emitter and the particle properties to give it the right shape so that it looks kind of similar to the scan line, and voila, we have an effect that works very well for a burning poster. Now let me show you how to use all of this in code. We call create portal opening animation entity whenever our poster gets detected. Here we create a plane of the exact same dimensions of our portal. Then we find the material we created in Reality Composer Pro. Once we find the material, we set its scanline parameter and its texture parameter. One important thing to note here is that I'm creating a texture resource with this image called image for Viz. Let's take a look at it. You can see that the image for Viz is actually the same image that we are using in our AR resource group. But the problem is that if we use the image from our AR resource group, it is going to show up as grayscale. So you have to create a copy of it and use that. Once we assign these properties, we are now going to create our model entity with this quad and the material that we just found. And then we'll add our portal animation entity as a child of our original portal quad. You can see here that I'm setting a subtle offset on the z-axis so that our portal animation entity is just floating over our portal quad. You can see here that I'm also adding the robot poster activation button here as a child of the portal quad. Let's see how this button was created. We can simply create this button as an attachment to our reality view. We can give it a name and some actions to execute as the button is pressed. And then in the make closure, we can get the entity for the attachment and pass it to the app model, so we can use it. Now that we have the entity for the attachment, whenever our poster gets detected, we can simply add our button as a child to our portal quad. We'll also find the entity for our particle emitter from our portal material scene and save it. Whenever the user presses the button, the activate robot poster function gets called. All this function is doing is animating our particle emitter entities and our scanline property in our material from top to the bottom of the poster. Well, the robot just standing there is not fun. Shall we make it move? Just to recap, our robot has an animation library component that has all the animations already added. So we have the dance animation, the idle animation, and then we have cut the jump animation into jump start and jump end. When the button on the poster is pressed, we call the animate robot entity function, and here we can simply create a sequence of all these animations and then play them on the robot entity. Let's see what happens. When you press the button, the robot will start doing its idle animation. Then it will do the jump. When it jumps, you can notice a problem over here that it's not really coming outside the portal. Let's fix this. To make the robot jump out of the portal, I added a portal crossing component on the robot parent. And then, where we are initializing our portal entity with the portal component, I'm adding some more parameters. The clipping mode here is specifying that we are using the plane of the portal quad and it clips when something tries to pass its positive z-axis. The crossing mode component is simply telling that anything with a portal crossing component inside the portal's world can cross when it passes on the positive z-axis on the plane of the portal. Now the robot can simply jump out of the portal. Now we need the robot to fall down on the floor, and we'll need plane tracking for that. Why do you need plane tracking, you ask? That's why. To do plane tracking, we are going to create a plane detection provider, add the plane detection provider in our run session function, and then we have to handle the anchor updates that the plane tracking provider provides us. Here I'm only going to process the plane anchors that are horizontal and also with the classification of floor. Then we create entities for the detected horizontal planes with a material, and then finally we give them a collision component and a physics body component so they can participate in collisions with our robot. We'll create another task modifier in our reality view where we are going to call the process plane detection updates function. I also made some big changes in the animate robot entity function. Here we cannot play a simple sequence right now because we want to handle events whenever a particular animation completes. Although this might look a lot of code, but all we are doing here is handling whenever a particular animation gets completed and then we trigger the next animation. To make the robot fall down on the floor, we are going to look for whenever our jump start animation completes. When that happens, we simply enable the gravity on the physics body component and also make the physics body dynamic. Then we subscribe to the collision events between the robot parent and our floor, and whenever that happens, we simply disable the gravity and make the physics body kinematic and play the jump end animation, so the other half of the jump. When that animation finishes, we'll make the robot dance. One thing I forgot to mention is the transition duration parameter over here. It is very cool because this will allow us to blend between different animations. Our robot now jumps down perfectly on the floor. Oh, our robot went back into the portal. Maybe Xcode can help us figure out why this is happening. What we can see here is when the robot is actually jumping out, the robot's entities transform is not really changing. So we need to add an offset to the robot when the jump ends, so the robot stays outside the portal. So we can fix this issue by adding a forward offset whenever our jump animation ends. And hopefully that will fix it. That is looking cool. But you know what will make it even awesome? A grounding shadow that will really make the robot feel like it belongs to our space. Let's add that. To add a grounding shadow, we need to add the shadow to the child in our entity hierarchy that has the actual mesh of the robot. So in this case, it's going to be this armature thing. I'm going to click Add Component and add a grounding shadow component. I'll make sure that Cast Shadow is checked. For the grounding shadow to be visible, our robot and our planes, they need to be in the same entity hierarchy. So here I'm going to make the content root the parent of our robot parent entity. This should give us the grounding shadow. Now I will also go and tweak the robot's position so it appears in the right spot, and then we can run it for one last time. Okay, so I tried something different this time and I really enjoyed it. I hope you did too. If something didn't make sense, please let me know down in the comments below. I'll catch you in the next one. See ya.